So please welcome Guillaume Lemaitre. He's a research engineer working at INRIA. He's a core maintainer of the project Scikit-learn. You may probably have heard of it. And he's going to present a nice feature that is going to be probably in the next release. And let's give a big round of applause for him. Welcome.
So thanks, everyone. I'm Guillaume Lemaitre. And here I will speak at the end of the talk more, because I want to somehow to see a use case where what I will speak will be useful for. But I will come at the end with the part of what will be the next release of Scikit-learn, hopefully. So before to start, I want just to give a bit of background about myself, because it will be actually useful for the talk. And the only thing that are interesting on that chart is before to start to work at INRIA in Paris, where I was a developer for Scikit-learn, I was actually working on a package called Imbalance Learn, because it was linked with my PhD. And so I will come back a bit later on that. But the idea was I needed that for my PhD at this time. So I will take the use case of imbalance classifications to later present the estimator that we have, because that's solving one of the problems. But before that, I want to discuss a bit about imbalance classification, because it's something that since years I'm working, or I work at some point. And for instance, what I was working on at that time was doing a PhD to detect prostate cancer. And you can see that it was a long time ago, because this is still a jet over a color map that you should not use anymore. And in those cases, basically, you have a very imbalanced classes, because you want to detect if a voxel is cancerous or not. And usually you have one positive voxel for at least 20 negative, okay? So when you have those type of problems, and that you are in PhD, the first thing that you go to the library to understand how do you find this, because people said that this is a problem. So you go there and you start to make research, and you find articles and review that say, balancing, you need some usually tricks, and then you need to do something about that. So you read about it, then you find methods that supposedly solve the problems, okay? And seeing that you're a PhD student, instead of writing paper, you write code, okay? And you write a library. So here it's just an example of how we could combine these things in Scikit-learn, so with resampling models and then a model afterwards, and make some cross-validation, and then we're happy with that, so we can manage that. And then, because you are a PhD student, you need to write papers, so you write a paper like this, so your supervisor is happy about it. And then you go in EuroSciPy in 2017 and you speak, use this package, this is useful, okay? And a few moments later, 6 years, take a bit of time, I come here and I say, actually, don't use that package, okay? So if I had to rename the talk here, it will be learning from imbalance data. I was wrong, but I was not the only one. Okay, so we have a lot of things that comes and that people believe, because the literature is written in such way that you should do in this way. And here I will come say, don't do like this, and I will show you why, okay? So the bigger claim that I have here is there's no problem of data balancing, okay? So we lied to you during long times. And one easy thing that you can imagine, like an easy statement, which I can find in another article that say exactly the opposite of what is written here. But for instance, that with resampling, by creating new data sample just randomly, actually you don't create new informations. So you cannot expect to just improve your predictive models. While if you read the paper of Smoot, it's exactly written the contrary there. But at least there is no theoretical background that says that. So here this is a strong claim. And I will try more or less to give a use case to do what usually the literature tell you to do. And then I will show you that actually that was not a problem. So here I'm taking the adult census data sets, where moreover, I make it more imbalanced to have one positive for 30 negative. Okay, so this is highly imbalanced problems. I will get normally some issues if I look at how people handle that. And here I give just like on the left side some information regarding the data that we have. So we have categorical features, numerical features, And what I will do is that I will do two scikit-learn models, one linear models, and one model based on trees. So like this, we have two families, one which is linear, one that is non-linear, and then we can start to make some comparison there. So how would you handle that? So I have my two, I will call those vanilla models. And it's just that I have a bit of preprocessing that I need specifically for the linear models, which is one hot encoding for the categories, and then standard scalars. And here I'm just using simple imputations, okay? Because I'm not interested, I will use the same imputation for every models. I'm not looking at that specific parameter here. And then for the random forest, I just need to use ordinary encoders for the categories, and then I'm good to go. So I could have used another model more powerful than the random forest, maybe the equivalent of so histogram gradient boosting in Scikit-learn, or that could be like GBM. I mean, this is the equivalent. But here, the nice part about random forest is that there's a specific method later on where people rebalance stuff. So like this, I can make a pure comparison of the same type of model, at least at the roots. And usually, if you go in the literature, we'll tell you, oh, so you can do cross-validations, but then you need a metric as well that should find or should give you an IDE or be insensitive to balancing. So the first thing that you will see is probably like balance accuracy. So I will come back at the end of the talk that you can question that choice, but here this is what we would tell you, okay? And if you run your experiments, the balance accuracy is known to be somehow random, let's say, a classifier that will predict the most frequent classes without any learning anything from the X data will perform at 0.5. So whatever you have above will actually, like, you start to learn something. So here I have two models which learn something, but is really not good. And actually, when you are PhD students, is where you realize that, oh, there's something wrong. I mean, people like publish paper with balance accuracy of 0.9, and I'm here, so there's something wrong, okay? So it's where you read the papers, and we tell you, yeah, use these amazing resampling methods, and everything will work, okay? So if I have a linear model, I can add a smooth, so I will come back in a minute what it is, just to give in a nutshell how this works. But this is an oversampling method that will try to balance your data. And in the random forest, I will use a balanced random forest which handle internally as well as the resampling. So how does it do that? So smooth, it's pretty easy, is I will create synthetic data based on canary search. And then between minority point, I will just create like random point here, I mean on segment. So what you can imagine here is that you can find just by the idea that you will have limitation that people don't discuss that shouldn't work in high dimensions. It will be very slow because you need to compare distance with a lot of things. So if you have 1 billion of points, that doesn't scale. You still create inside radius. So is it a good thing or not? I mean, it's questionable. But still, people say that's what you should do. And then in the balanced random forest is just a small like difference with the random forest where for each bootstrap, you will actually take a bootstrap of the majority of the minority points, and otherwise you draw with replacement on the majority one. So like this, you have two. Each bootstrap is actually balanced, and then you construct a tree. Okay, so you have all your tree like this. So if I evaluate those, then things start to work. I have stuff that people publish, and now I'm like around 0.8, and everything works. Okay? So yes, but actually people just overlook what they are doing. Somehow you didn't go deep into like what are the consequences of doing so. So there is two main things. One is the resampling strategy actually optimum for the metric that you are using? And here there is nothing, when I did my balanced random forest, there is nothing that said, actually I try to optimize my balance accuracy or my ROC AUC or whatsoever. So there's nothing driving basically the resampling, okay? And then there's a second thing is like this resampling have actually an effect on the classifier. And the effect is the following, is that you are breaking the calibration of the classifier. So what is calibrations? So in blue, I have the vanilla logistic regression and random forest. On the x-axis, what you see is the output of predict proba of the classifier. And what you would expect if a classifier tell you you have 10% chance to be class 1, it means that on a test set, what I expect is if I have 100 points, I have 10% of the point that should be 1. Okay? So that's what you expect with the calibrations. And what you see is that if I resample, the only thing that I do is that I'm making my classifier in terms of probabilities overconfident. So now it will start to tell me I have much more events that happen, much more cancerous things, because we just like remove a lot of negatives. So the probabilities are wrong. Okay? So if you try to use those probabilities, they are not meaningful anymore. And the only reason is because in Scikit-learn we did something wrong, is that we force the decision threshold to be always at 0.5, while actually this is something that we should be tuning, okay, and moving depending on the type of decision that you want to do, okay? And this is where basically what I will present here, it will be an estimator where we retune this decision threshold such that you don't touch the probability, you fit a good probabilistic models, and then you just change the decision towards a metric that you want. So if it's balance accuracy, that will be balance accuracy, but if it's any other metric, a business metric, you should be also able to do that. So this is living inside this PR now, but you can already see there's documentation and everything. So here I will just, maybe it will be called in another way, we never know, but I mean, that's a review part of the process. But hopefully it will be inside the next release. And the way that it works is that, so this is a meta-estimator where you will pass your normal easy models. So for instance, my vanilla logistic regressions or my vanilla random forest there. And then I will provide the objective metric that I want to optimize and then find the threshold that corresponds, okay? So there's a lot on that slide, but so I will go like element after element. So what I expect here is that on the left, this is a curve which we actually optimize. So this is a balance accuracy for the different level of probability. And what we can see is the triangles, which is on the top, is actually the point that I find when I find the optimum values. And you can see that in terms of balance accuracy, it's much higher than the default, which is 0.5. So my vanilla model. And that's why here, not tuning it, that's why I have a bad score, okay? And the middle one is like the ROC curve. So why I put a ROC curve is to make understand that before and after tuning, you don't change the ROC curve. Okay, this is the same. The probability of the model are exactly the same. Okay, the only thing that you change is you switch the cutoff points, the decision points, basically on that curve. Okay, and you can imagine that if I am a doctor or whatsoever, I can actually want to choose a point because I want more false positive or less false positive. And this is part of your metric as well, okay? So it depends on what you want. So here, I optimize with the balance accuracy, and then I look how it changed. And at the end, just to convince myself that I'm doing something, I look at the confusion matrix. And on the top, this is the default one, and on the bottom is one that I switch my threshold, and we can see that we have much more true positive at the cost of, I don't know which one is it, on the top right, so either for positive or for negative, I never remember. But somehow it is something that the balance accuracy considered this is a trade-off, and this is fine to make mistake there, okay? We would have another metric, we would have another trade-off, okay? That if I try to optimize something, it will impact basically the confusion matrix in some overall. Okay, so now that I show that you can do that, let's take my two vanilla model, let's put them there, and let's see what are the results, okay? And now I get like at least good result for the logistic regression, which is more or less the same, and almost as good results as for the balance accuracy. And normally you should come here and you say, okay, 20 minutes, that's 20 minutes that you speak, and you say it should be as good, and this is not, okay? And the issue is that I forget what the most important thing in machine learning is hyperparameter search. So change stuff, I forget to change stuff and like find like what are the best parameters. And the little change that you see here, like why I'm worse, it's just because of that, okay? So let's do some grid search and some optimization. And this is something that I have really to stress. It's not only doing the tuning of the the decision threshold, but as well of your model. Always tune the model. So, strong recommendations. Don't use the default of Scikit-learn, which usually use the accuracy, and usually intuitively what you will use is actually a thresholded metric, so balance accuracy, precision, recall, or whatever, okay, to make you research or you randomize search. Don't do that. Instead, do an unthresholded probabilistic metric, or what we call as well a proper scoring rules. It's even better. So here, for instance, the log loss, because the thresholding will imply that you can have a model with the same accuracy, but if you look at the true scoring rules, because you have more detail about the probability, actually you will see a peak on the left-hand side of the things. So for instance, here we search for minimum, so there's a minimum clearly there. Why on the one you can have, like, for instance, a plateau. And here we can even see that this is not at all correlated, okay? And seeing that what we want to have is actually, let's get the best calibrated classifier that we can get. So let's do the left, and then we can tune basically the thresholded metric, okay? So here if I take the vanilla random forest and the balanced random forest, because I need to optimize both, and I look at the log loss, I have like two different things. So for instance, here I will see that if I check the minimum, I should have the max number of leaves inside my tree should be around 200 leaves. And if I look at the balanced random forest, which is actually interesting, so first, like, the log loss is much higher. So this is the impact of the resampling here, is that I will never get as good probabilities as my overclassifier. And is what we see actually in the calibration curve, okay? You completely broke this. And then the second thing is the resampling. You see that you have a curve which here then have a plateau. And it's because we remove so many basically samples that after that point, probably we don't create new leaves, okay? Because we have like, the resampling plays a role of regularization for my model here, okay? So seeing that is not the case on the left, then I need to find like the exact number of leaves that I need to not overfit. And if I do that, so here that was the previous thing, so I said here this is a bit worse, I become as good as a balanced random forest, okay? And here I control for everything. And this is a simple case where I can find even worse example where the sampling method are much worse than like the post-tune one, okay? So here it's just like, it was to make it easy to understand, okay? So now there is a question, why balanced accuracy? And accuracy is no reason, I mean, you are a data scientist, you open the thing, we tell you use that. But if you have inside a company, the people will tell you, yeah, but I mean, at the end of the money, of the day, I want to make benefit. I want to have profit, okay? And then your metric here, probably that you want to take decisions is business driven, okay? And now, so what this estimator allow is actually to do cost sensitive learning. So it means that our metric is based as well on some external data. And to do that, you need as well like something that we'll see in Scikit-learn in a second. So here I will just take like a case of credit fraud card, and somehow you can have a cost benefit based on basically the transaction that you have. So if you have a good transaction and it was legitimate, then you gain a percentage of the amount that people just like withdraw money or make the transactions. If actually you accepted a fraudulent transaction, then you lose the money, and then you have maybe a more complex thing for the two others. So what is very important here is that the amount that you have is not a feature from your data. It's just like an external, which is neither in X, of like the feature that you have that you want to learn from, neither what you try to predict. Okay, so it's some like metadata on the side. And what Scikit-learn did like recently is that we implemented something which is metadata routing that allow to pass those metadata to models, scoring methods that can be used to evaluate or to drive the fitting of an estimator. And it's exactly what we want here. So here I define a business metric, so you can just discard what is inside the middle of the function. This is exactly what I show inside this confusion matrix, okay? But what is important here is that you have the true values, and then you have an amount, okay? And this is my metadata that I want to pass to this scoring. And how do I get there? So you have this new feature that you can normally already do, but we don't have like implemented for all the estimator. But next release that will be there. So you can enable this routing, and then you can start to say to, for instance, some scoring function, use these meta informations. We will provide it to you, and then you have to use it. So for instance, here we create a scorer where we say, when you will use this scorer here, please, we will send you a new information, which is an amount that corresponds to what you have inside the signature here. And how do you use it is you call these scorers, then you provide the model that you want to evaluate, the data that you want to test on, and then you provide this extra information, which is just like an array that have the same size and that you want to use, okay? And how do I use it inside my model here? For instance, instead to optimize for the balance accuracy, I want to optimize for that specific metrics. So then I just need to pass this scorer to the objective metric. And then I do a fit, and at the moment of the fit, I'm just passing my extra data. And when I'm doing my testing, then I'm passing the test data. Okay? And this will be under the hood, like provided to the scorers that allows basically to do these things. And finally, what you get is like if you do a cross-validation and where you pass these informations, if I compare a vanilla logistic regression with a post-tune logistic regression, then I can see that, oh, by optimizing the profit, then I get a much better classifier, and I know in dollars how much I do better, okay? And here, this is a business metric oriented, and we are closer to the marketing or to like to the product part, okay? And we don't just like send some raw KUC to people, okay? So, takeaways: stop to try fighting balancing with resampling, okay? This can be still useful for some cases. For instance, you want to run on some smaller sets, but then you mean that you need to recalibrate your classifiers. You can still use this. I mean, there's still some use cases, but not for the one that is written inside the literature, okay? Instead, what you need is absolutely tune your hyperparameters with this param or without that params. Okay, so this is like the main thing. It's like tune the hyperparameters, use a proper scoring rule for that, and then tune the decision thresholds when you're inside the case of binary classification, for instance. And then, just for a 3 point, always cross-validate. Okay. And that's it. Thank you. It's broken.
Okay, good. So we have enough time for a few questions, happily. Okay.
Thanks, Guillaume. Really fascinating material and nice talk. Practical question. So we are here in bullet point 3, tuning the decision threshold. Is this something you can implement or would you recommend implementing this in a grid search fashion controlled by some sort of cross-validation, or can you do this post-hoc?
You can do both. So now, should you do it inside the threshold? So if you do it inside the grid search, then you can investigate all the model that you have inside the grid search and see what's the influence of changing data and what's in the if your decision threshold change. So that's a very good way of analyzing what is done. At the end, the model that you put in production will be a single model, then you need to fix once. But I think that inside your pre-analysis before deployment, I think it's a very good thing to actually maybe tune that and see how that moves, like any other hyperparameters. This is just an additional hyperparameters.
Hi, thanks for the presentation. If you started the comparison using the log loss instead of the balance accuracy, then would you have still needed to find the tuning that you did based on the threshold, or?
So the thing is like the log loss of the models will be, I mean, with the vanilla model or without the vanilla model is exactly the same because I didn't change that, okay? So basically it's like if you're interested about probabilities and the log loss just referred to like that specific thing about like probabilities. then if you do resampling, you still have that issues that the resampling will have a worse log loss. But probably if people would have used the log loss from the beginning, they would have seen that there is no problem of like resampling problem of imbalanced problem. The problem that you have is where do you put the result? And somehow is like the flexibility with the decision things.
Do you maybe think, I mean, I don't work often with classifiers because for me, like regression or classifier, I mean, it's just random variables with a different distribution, so Bernoulli distributed. I would have normally started with log loss because I would have started from Bernoulli likelihood just to think like that and not converting probabilities to integers 1 or 0.
I agree this is what you should do, but I can tell you it's not what the literature actually do. So that's why I'm here to tell you, don't listen whatever you hear, because people will say. And because it's more intuitive. At the end, I want to make as well a decision, and some people are just interested about the decision. So at some point, you will result the probabilities. So you need to know how to do that.
Yeah. I totally agree also for then the metrics which require to have, I mean, 1 or 0 as predicted values.
Yeah.
Thanks.
Who else has questions? What? So clear?
Okay. Thank you.